Our final example problem for this unit of study on work, kinetic energy, and power comes from the AP Level C exam from the year 2003. So we're told there's a 100 kilogram box being pulled. The way in which it's pulled is with a varying force, so that the position as a function of time comes out governed by this expression. Now, before I even read through all the questions A through D, I'm just going to take the time to do a little calculus and find out what's an expression for the velocity of the box as a function of time. So all I have to do is take the derivative of position, which gives us 1.5 t squared plus 2. And while I'm at it, I'm going to find acceleration, which is the second derivative, or the first derivative of velocity with respect to time. And this gives us 3t. Okay, and now let's look into this in greater detail. What do we have to solve for? A, determine the speed at time t equals 0. So fortunately, we have this expression for velocity as a function of time, and all we have to do is plug in t equals 0 to the equation v equals 1.5 t squared plus 2. Well, at time t equals 0, this term goes to 0, so the initial velocity is 2 meters per second. Part B is threefold. We have to find kinetic energy, force, and power, all as functions of time. So first things first, let's find kinetic energy as a function of time. When I think of kinetic energy, I think of the equation 1/2 mv squared. And the mass is 100 kilograms, so 1/2 m. 1/2 of 100 is going to give us 50. And then v squared, well, we have an expression for v, 1.5 t squared plus 2, and velocity has to be squared. So there we have it. Kinetic energy as a function of time is 50 times 1.5 t squared plus 2 quantity squared, and we can leave it at that. The next question was find force as a function of time. Now when I think force, immediately I think of Newton's second law, F equals ma. The mass is 100 kilograms, and the acceleration, well, we found an expression for that as well. So this is 100 times 3t, so it's simply 300t. F equals 300t. So indeed, kinetic energy is a function, or can be expressed as an equation based on time, and same with force. So lastly, we have to find power as a function of time. Now when I think of power, I think of work divided by time. Well, actually, that's a way to calculate average power. And if we want power as a function of time, we're definitely interested in instantaneous power. So that makes me think of the dot product of force with velocity. Now in this case, the object's going to have a velocity vector to the right, and the force that's applied is to the right. And so we really don't have to consider the vector nature of this dot product. We can just say it's the magnitude of the force times the magnitude of the velocity. Well, let's see. We just found the force in the previous example. That's 300t. And velocity, we have here 1.5 t squared plus 2. So if we multiply that out, instantaneous power is 450 t cubed plus 600t. Okay, moving on. Part C, calculate the net amount of work done from 0 to 2 seconds. There's a couple ways we could solve for this problem. Let's see, the first thing I'm thinking is that average power is work divided by some relatively large time interval. Instantaneous power is the derivative of work with respect to time. It's the instantaneous rate of change of work, or rate of change of energy, rate of work done. That means a little bit of work done is equal to the instantaneous power acting over some infinitesimally small time interval. So if I want to find total work done, I need to add up all of the incremental bits of work that are being done, which means take the integral of p dt. So we can find the net amount of work done by taking the integral of 450 t cubed plus 600 t from 0 to 2 seconds. If we think of integration as the antiderivative, that this means work is equal to 450 over 4 t to the fourth plus 600 over 2 t squared evaluated from 0 to 2. Now evaluating it at the lower limit's easy because when we plug in 0 for t, we're just going to get 0. Okay, so the work is equal to, let's see, 450 divided by 4 would be 250 divided by 2. I guess that's 112.5. And then times 2 to the fourth plus 300 times 2 squared. 2 to the fourth is 16. 2 squared is 4. 112.5 times 16. Grab a calculator, see what you get for that. You get the same thing as me, 1,800 joules, and 4 times 300, that's 1,200 joules. So you get that the net amount of work done is 3,000 joules. But I said there's two ways we could solve for this, and that's nice. If both answers come out to be the same, we can be certain that we got it right. So we also know that work is equal to change in kinetic energy. Or in other words, it's the final kinetic energy minus the initial. So let's find the initial kinetic energy. That's 1/2 mv initial squared. So it's 1/2 times 100. Remember the initial velocity was 2 meters per second. Okay, so this is equal to 200 joules. So now we need to find the kinetic energy at time t equals 2 seconds. Well, we have a formula for kinetic energy that we developed here. Kinetic energy is, well, we can copy this. Okay, so our kinetic energy at time t equals 2 seconds is 50 times 1.5 times 4, right? 2 squared gives us 4. Plus 2, all of that squared. 1.5 times 4 is 6. 6 plus 2 is 8. 8 squared is 64. What's 50 times 64? That's the same thing as 100 times 32. That gives us 3,200 joules. So, change in kinetic energy is 3,200 joules minus 200 joules, final minus initial, which, oh, hallelujah. That gives us 3,000 joules. Same thing we got in our first attempt. Part D. Indicate below whether the work done on the box by the student from 0 to 2 seconds would be greater than, less than, or equal to the answer we just found. Well, let's see. The box slides across a rough surface. So the amount of work that's done by the student is not the same as the net amount of work, because the net amount of work is work done by two forces, right? Well, let's see. Let's make a free body diagram. There's normal force and there's mg. But neither of those do work because those are forces that are perpendicular to the displacement. So the person pulling it gives an applied force, and then because it goes across a rough surface, there's a friction force. So the applied force is going to do some positive work. The friction force is going to do some negative work. And the net work is the combination of those, right? So if we want to be explicit here in our answer to part D, the net amount of work is equal to the positive work done by the person plus the negative work done by friction. So if we rearrange this, we'd say the work done by the person is equal to the net amount of work plus the work done by friction. And so the work done by the person would be greater than the net amount of work. Thanks for watching.